Okay, statistics, AP statistics, sorry about that. We are going to interpret some sample computer output now. So I've got several different examples here. This first one is a regression analysis from computer output known as jump in. This next one is going to be from a company called Minitab, or a program, sorry, called Minitab. And then this last one is going to be from Datadesk. Now, when you run off to college, your university or college will have access to some kind of a computer program for statistical analysis, etc., etc., because they, you have to pay to go there. They can afford it. These programs are really expensive. That's why we don't have any, because we're a high school. But more often than not, on the AP test, you're going to be given some computer output and you're going to be asked to write the LSRL from it, interpret slope, etc., etc. So how do we do that, Ms. Griggs? Well, let's look at this. All right, a linear model is created using sample temperatures in Bismarck, North Dakota, to predict temperatures in Buffalo, New York. I'm going to stop right there and we're going to talk about something. If I am predicting temperatures in Buffalo, New York, then that means that Buffalo is my Y value. Okay, it is my response variable. So I've already got part of my equation. I am predicting temperatures for Buffalo using the temperatures from Bismarck, North Dakota. All right, how am I going to read this? What all do I need to see in my computer output? Well, there's a lot of stuff going on. There's good news here. You're not going to use most of this. In fact, you don't need any of that. Now later in the year, right at the end of the year, we will talk more about computer output and some more of this stuff will be important. But for now, not a whole lot going on here that you need. All right, the most important thing we need to write our LSRL is the slope and the y-intercept. So I need my slope. Actually, I'm gonna just need my slope and my y-intercept. Okay, so if I know that my slope formula looks like this, the number associated with x is the slope. The number associated with y is the y-intercept. So let's listen to that word, intercept. See right down here where it says intercept? The number right next to intercept, yeah, that'd be the y-intercept, kids. What? That means the other one, Bismarck. Okay, Bismarck is going to be x because it is my explanatory variable, because I already established that Buffalo is my response variable. So since Bismarck is my explanatory variable, the number right next to it is the slope, because in my equation, isn't slope right next to my explanatory variable? Yes, it is. So now I've got all the information I need to write my least squares regression line. So because these numbers are really long, I'm not going to have room up here. So I'm going to write this down here. So Buffalo temps. I'm going to predict those with, I've got my y-intercept plus Bismarck. Groovy. So that is my LSRL right there. What else can you get from computer output that we might need? See this right here? R squared. That's R squared, or the coefficient of determination. So r squared is this 0.99 right here. And if I wanted the correlation coefficient, which is r, I would simply take the square root of this. So r is, let me get my handy dandy calculator, and we will just figure that out. Thank you very much. 0.990044 square root 0.995 and some zeros, blah, blah, blah. Okay, so why would I need these? Well, because we're going to learn to interpret all of these things. We're going to learn how to interpret the correlation coefficient, the coefficient of determination, the y-intercept, the slope. It's just magical. Okay, so let's go on to the next computer output, Minitab. Minitab's the one you want. I mean, they give you the equation, for crying out loud. All right. So they do word things a little more, or a little differently. This time they call the y-intercept the constant, which makes sense because in the equation it is the constant value, and they give you the coefficient right here. And then Bismarck, of course, is still my explanatory variable, so slope is still associated with it. So that goes right there. And then again, they give you r squared, but we need to talk about something. They also give you r squared adjusted. We don't ever use adjusted. Also, it's important to point out, see this s right here? A lot of kids think that's slope. It's not, okay? That is actually the, has to do with residuals. So we're not going to deal with that right now. Okay, so that's Minitab. All right, Datadesk. What does Datadesk look like? Well, Datadesk has some interesting features. It tells you right up front what your dependent variable is so that you can go ahead and prepare to write your LSRL. Oh, that was horrible. That's better. All right, so where is this going to be? Constant? 23.5915 plus Bismarck, there's my slope right there, 0.740767. Oh, I ran out of room. Story of my life. Bismarck, there we go. So again, same information, just a little bit different view here. And then, of course, they give you r squared again and adjusted, but we don't deal with that. So we can get r from r squared by taking the square root. And, of course, this one has given you the scatter plot and the residuals. So let's look at the residual plot. The residual plot is scattered, so that's good. Okay, we don't see an overall repeating pattern in it. So the residual is nice and scattered. That's awesome. If r squared is 0.99, then if I take the square root of that, I am going to get 0.995, just like I did earlier. So if I have a residual that's scattered and I've got a correlation coefficient that's that close to 1, that should make perfect sense to you, because see how very nearly linear that is? Those points are not scattered around very much. So the idea of this correlation coefficient being so close to +1, I have a nice scatter plot that's very linear, and I have a scattered residual. A linear model is an excellent fit for this data. That's what all of that tells you. Magical. All right, so I am going to interpret some of this stuff in another video because this one's already too long.